Adelante.
Hello.
¿Está grabando?
Where's the screen?
Yes.
Yes.
Go on, please. Yes.
Okay.
We're recording.
Thank you very much. Hello, good morning, everybody. Thank you very much for being here again for this another colloquium from the Severo Ochoa program. Today we have the pleasure of having here Dr. Shane O'Sullivan. So first of all, thank you very much for having accepted our invitation to be here today. And thank you all of you for being here as well, here or online. Shane O'Sullivan is a radio astronomer working at the University Complutense de Madrid under the program Atracción de Talento Investigador from the regional government in Madrid. He got his PhD in 2010 from University College Cork in Ireland on the topic of VLBI observations of IGrM jets. He spent 5 years as a postdoc in Australia on science related to the ASKAP-POSSUM survey, where POSSUM means polarization survey of the universe's magnetism. Since then, he has worked in UNAM, Mexico City, Hamburg Observatory, and Dublin City University. He works on understanding radio galaxies, the cosmic web, and the origin of cosmic magnetic fields. He's the co-PI of the LOFAR Magnetism Key Science Project. And today, as you know, he's talking about the magnetized intergalactic medium revealed by the SKA Pathfinders. Thank you again, Shane, and welcome. So the floor is yours.
Thank you very much for the very nice introduction. Yes, so today I will talk about trying to constrain the properties of the intergalactic medium and its magnetic field through radio telescope observations with these amazing new Pathfinder and precursor telescopes we have in advance of the square kilometer array. And before I start, I'd like to just acknowledge the huge amount of work of many people over many years, which will be the basis of some of the results I present here within the LOFAR surveys and magnetism key science projects. And also towards the end, hopefully I'll show some of the new results from this ASKAP, so this Australian square kilometer array Pathfinder telescope, and a new survey that's recently started. Okay, so I was wondering when the last time I was in Granada, and yeah, interestingly, it was exactly 11 years ago to the day that I also gave a talk at this very nice AGN Jets meeting organized by Jose Luis Gomez and others. And yeah, so I have very nice memories of this, the last time I was in Granada, visited lots of nice places, and yeah, the conference was a really great meeting. Okay, but today, so I'll be talking about things on larger scales, or on the largest scales in the universe. And just to start with, I wanted to give some kind of big picture kind of motivation without maybe much explanation at the start, but hopefully as I go through the talk, things will become clearer. And so what we've been finding recently is that through the use of this Faraday rotation effect, we're actually able to trace, or finding it to be quite a sensitive tracer of the large scale matter outside of the halos of galaxies in the cosmic web. And so there's been a few recent publications showing how you can use Faraday rotation to trace ionized and therefore magnetized gas in the outskirts of clusters, and also at the interface between the intergroup medium and the intergalactic medium. And we've also excitingly found some signature of the circumgalactic medium in nearby galaxies. And this is important because it helps actually constrain these impressive MHD, cosmological simulations and galaxy simulations on scales that are not very well constrained to date. So beyond the actual, stellar disks and halos of galaxies, so that we can hopefully provide some new constraints on these models to actually help better characterize the circumgalactic medium as well as the intergalactic medium and the effect of galaxy and AGN outflows on the large scale structure of the universe. Okay, and that's one key motivation. The other one then is actually studying the magnetized properties of filaments and voids of the cosmic web to actually try to infer the origin of cosmic magnetism. So whether it was there from very early on in the universe, or whether it's mainly been produced on small scales later in the universe and then expelled into the intergalactic medium. And this has quite, very interesting implications if there are strong primordial magnetic fields, because it gives us a unique insight into the physics of the very early universe. So, for example, if the fields were generated during the epoch of inflation, then we have this kind of unique probe of that period of the universe that's otherwise very difficult to study. And what's exciting is that if you do produce primordial magnetic fields in the very early universe, it can also produce the same, or it's consistent at least with the production of these gravitational wave background that I guess is normally attributed to supermassive black hole binary systems. And the same magnetic fields that produce this stochastic wave or stochastic gravitational wave background can also potentially alleviate this Hubble tension that you may have heard a lot about, by actually the presence of these magnetic fields means that recombination occurs a little bit earlier, and this helps then to actually push the Hubble constant to a larger value that's more consistent with the local universe measurements. And then, if you have these magnetic fields produced before structure formation, then they actually they change the matter power spectrum on the small scales. And this can lead to the production of more dwarf galaxies than normal, so that it affects the whole history of reionization as well. So these are kind of two of the main motivations for why it's interesting to try and constrain the properties of the cosmic web on these large scales. And so we know a lot from simulations, or at least we think we know a lot, based on how matter is distributed in the universe. So all our measurements are usually confined to the quite close to galaxies, at least in the local universe. But we know that the majority of normal matter actually exists beyond beyond galaxies in the filaments and voids of the cosmic web. So it's just this diffuse ionized gas, mainly in the local universe, just filling this cosmic web. Yes, and evolving kind of along with the collapse of these structures. And then what we've been finding in recent years that this large scale structure is actually appreciably magnetized. And so both from measurements of synchrotron radiation of accretion shocks in these filaments, as well as Faraday rotation measurements implying the existence of magnetic fields in these filaments. And also from gamma ray observations, it appears that the voids of the cosmic web are also magnetized. And so then the question arises, what's its origin? So how were these fields actually produced in the first place? So it's very difficult for a galaxy to pollute a whole void of the universe with magnetic fields. And so most people are, the consensus maybe to date is that it's most likely that there's quite a significant primordial field that has produced produced the magnetic fields we see in voids, possibly in filaments, and then we have to understand what the contribution of galaxy and AGN outflows then are to these regions as well. Okay, and so in terms of numbers of what we understand to date, so we have some upper limits on the co-moving magnetic field strength at the epoch of recombination. And so from these anisotropies in the CMB temperature map, you can constrain the magnetic field on megaparsec scales to be less than a few nanogauss. And so these are pretty robust upper limits on the strength of magnetic fields in that epoch. And then excitingly, in the last 10 years or so, people have found that you can provide lower limits So that's really saying that the universe is magnetized on the larger scales from these very high energy gamma ray measurements from blazars. And so this is a pretty neat process where you have these high energy tera-electron volts and tera-electron volt gamma rays that pair produce off the extragalactic background light. And then these pairs scatter or upscatter the CMB photons to giga-electron volt energies. And so then you expect this excess of giga-electron volt gamma rays associated with these TeV sources. However, this is not seen to the level that's expected. And so the implication then is that these electron-positron pairs, when they're created, are actually deflected away from our line of sight by the actual magnetic field in these voids. And so then you can put an upper limit of, say, 10 to the minus 7 nanogauss, or sorry, lower limit of 10 to the minus 7 nanogauss in these voids. Right. And so, and then the way, so, okay, this is quite a large range of uncertainty. So we have 7 orders of magnitude, unconstrained parameter space. But how we actually distinguish between primordial and what we call astrophysical mechanisms for the origin of cosmic magnetism. By astrophysical, I just mean that the fields are created on small scales, amplified within stars, galaxies, and then ejected into the intergalactic medium. So it's kind of like a pollution of the intergalactic medium from these astrophysical sources. All right, and the magnetic field, measuring the magnetic field then on these larger scales is actually key to distinguish between the two scenarios. Because, yeah, we have lots of nice measurements of the magnetic field in galaxies and galaxy clusters, but then we're lacking information on scales of filaments and voids, whereas the astrophysical scenario, you expect the magnetic field strength to fall off quite quickly away from these overdense structures. But for a primordial field, then you expect that there's appreciably larger signature of these magnetic fields in the voids and filaments. And so this is how we hope to distinguish between these two scenarios. Okay, and before I go too much into the details, I guess maybe it's not necessary here, but just to give you a brief overview of how we are studying magnetic fields with radio telescopes. So one of the key mechanisms is by using synchrotron radiation. So this is this very beautiful Fornax A radio galaxy. The orange here is the radio synchrotron emission. This is the host galaxy here in the optical. And so we know that we have appreciable magnetic fields in these radio galaxies because they're producing the synchrotron radiation where you have these relativistic electrons spiraling along around magnetic field lines and producing this synchrotron radiation, which gives us information about the magnetic field in the plane of the sky. But for this talk, unfortunately, I'm not going to be studying the details of these radio sources or saying much about them. We're just using them as sources of linearly polarized radiation. So synchrotron radiation happens to be highly linearly polarized. So for the purposes of this talk, we're just using them as sources of this linear polarization, which allows us to measure the Faraday rotation all the way along the line of sight. So we have our source of linearly polarized radiation. And then once you pass through a region of ionized and magnetized gas, you encounter this effect of Faraday rotation, where the amplitude of the effect is related to the rotation measure, which depends on the free electron densities and the magnetic field along your line of sight. So this is a Faraday rotation measure map of the same radio galaxy. You can see that there's lots of small scale structure here that's actually associated with the source itself. So the interaction between the source magnetic field and its environment. But for this talk, we're mainly interested in just the average magnetic field, or sorry, the average Faraday rotation, which tells us about the magnetic field properties along the line of sight. And so one of the key goals for, well, eventually the SKA, but also SKA Pathfinders, is to produce this Faraday rotation measure grid. So just you have as many Faraday rotation measures as you can measure across the sky. So finding as many polarized, linearly polarized radio galaxies as you can, and then converting these beautiful radio galaxies into little circles. So just taking, where you detect the polarized emission, and then taking the average Faraday rotation of that single source. And then you have this whole map or grid across the sky of your Faraday rotation measure. And we use this for, as a statistical probe of foreground Faraday rotating structures. Okay, and so there's two main regimes, I guess, where we construct these Faraday rotation measure grids. Historically, it's mainly been done at centimeter wavelengths, where it's easier to measure the polarization of sources and their associated Faraday rotation. And as I'll talk hopefully towards the end about this new survey with the Australian SKA Pathfinder, which is finding an incredible 30 to 50 Faraday rotation measures per square degree, whereas in the best previous large area survey provided about 1 rotation measure per square degree. And there's also a very good error in the Faraday rotation of 1.5 radians per meter squared. This probably doesn't mean too much to you now, but hopefully later. But these centimeter wavelength observations provide a really broad opportunity to study magnetic fields in a wide range of environments. But most of my talk is going to be studied on constructing Faraday rotation measure grids at meter wavelengths. So this is relatively new. So just in the last few years, we realized we could do this and that it was scientifically useful to do it. And so with this LOFAR 2-meter sky survey, we're finding about 0.5 RMs per square degree, so a much lower density. But the key point here that enables us to actually do unique science is that the uncertainty in these rotation measure values are then very, very small at these meter wavelengths. And this turns out to be a very key probe of these very diffuse and weakly magnetized environments, such as the filaments of the cosmic web. Okay, and so the basic idea of the experiment that I'll be talking about is we have these bright sources of linearly polarized radio emission, so this radio galaxy at some redshift, and then as the light propagates through the intergalactic medium, so it encounters some region, some filament of the cosmic web that has a certain gas density and a magnetic field, and then it encounters some Faraday rotation. And then it might pass through many filaments, and it's the integral of all these contributions along the line of sight. And so how we measure it is in the change in this linear polarization angle is proportional to or is equal to the Faraday rotation measure and the wavelength squared. Right. And so for any one radio galaxy, we can't distinguish, what's happening along the line of sight. But so we aim to do this in a statistical sense with many of these sources. Okay, so to give you some context on, what a particular value of the rotation measure actually means. So if we're looking at these intergalactic filaments, then what's the typical value? So if we take a particular overdensity for these cosmic web filaments and a particular path length and a magnetic field strength, then we end up with something of order 1 radian per meter squared. So this is the type of value that one would expect for the contribution of filaments of the cosmic web. So it's relatively small in the sense of how we measure Faraday rotation and what our typical uncertainties were. But if you remember from the previous slide or 2 slides ago, the uncertainty with LOFAR is much smaller than it was with the centimeter telescopes. Because 1 radian per meter squared, so it rotates the linear polarization angle by about 2 degrees at centimeter wavelengths. And so that's measurable, but it's challenging. But at meter wavelengths, because if the effect goes as wavelength squared, you actually rotate the polarization angle by 200 degrees. So this means it's just much easier to measure very small Faraday rotation measure values, and you get much higher precision. Okay, and this is why we want to use this SKA Pathfinder known as the low frequency array, or LOFAR. And so hopefully you've already heard of LOFAR. Oh, can I get this? So this is a pan-European radio interferometer operating at very low frequencies or at meter wavelengths. And so to date, we've mainly been using the data just from the inner 100 kilometers. So all the stations within the Netherlands. But in the future, we hope to actually use the full power of the array to image at the highest angular resolution. And so we have these large collaborations. So the magnetism key science project and the surveys key science project in terms of the continuum imaging of these data sets. Right, and the main project here, or the main survey, is this LOFAR 2-meter sky survey. So it's operating, or the survey is operating from around 150 megahertz, and is a very sensitive radio survey for typical radio galaxies that have these deep spectral indices. Sorry, I didn't explain that at all, but for typical radio galaxies, LOTS is very sensitive and comparable to these SKA Pathfinder telescopes at centimeter wavelengths. So this red and blue line means the spectrum of a typical radio source. And so we've had a data release 2. So the aim is to cover the whole northern sky, but we've had a data release 2, which is about 27% of the northern sky. And we're mainly avoiding the galactic plane because it's very difficult to produce images there. Okay, and so we have these 2 fields. The data are publicly available, so you can see the LOFAR surveys webpage and the associated publications that not only give you the radio information, but also the multi-wavelength information associated with each of these radio sources. And yeah, impressive 4.4 million total intensity radio sources are cataloged. And for my particular interest, the bright ones are the ones that are detectable in polarization. So there's about 1 million or so of those. But we only find about 2,500 linearly polarized sources. So it's a lot of work to search through the whole survey to find only 2,500 sources. So this means only 0.2% are detectable. But thankfully, with this 0.2% that we detect, we can actually do interesting science because of this excellent precision. Okay, and the survey is continuing. So if your object of interest lies outside this publicly released data, then please do get in touch. And it's probably advanced a bit more. By the end of the year, we will have covered basically the whole northern extragalactic sky, just minus some regions of the galactic plane. And that will be part of the data release 3. Okay, and so what I've been doing for the last number of years is to then, do this rotation measure grid for this LOFAR 2-meter sky survey. And so, we've taken these beautiful radio galaxies, as shown in the bottom right here, and some portion of that radio galaxy will be linearly polarized, and we can measure its Faraday rotation, and then we represent it by one of these small little circles. And so each of these circles corresponds, to this Faraday rotation measure, where the size of the circle corresponds to the magnitude and the color corresponds to the sign. So we're sensitive to the actual line of sight and the net line of sight magnetic field direction from this Faraday rotation as well. Oh yeah, so this is just a zoom in view. Oh yeah, so here you can see the different sizes of the circle and the Faraday rotation measure values they correspond to. And so what you can probably see immediately with your eyes is you have these large coherent patches of sign. So you have these, this very nice blue kind of filament that's coming along here. And so this is representing the dominant mean contribution from the Milky Way magnetized interstellar medium. And so to study the extragalactic Faraday rotation, we actually have to remove this, what we call the galactic rotation measure. And so we do this with, a model. We have a model basically that uses the Faraday rotation measure and smooths them on large scales. And we hope that then this actually accurately removes the dominant or the main contribution from the Milky Way. And all that we're left with is this residual Faraday rotation, or this residual rotation measure, which should be dominated by the extragalactic component. And you can see that now all the nice patterns have gone away, and you just have this kind of random in the sense of the line of sight component across the sky. And so what this looks like in a histogram, so the colors are just the different fields because they're in different areas of the galaxy. So you just have some initial distribution of RMs that's related mainly to the Milky Way. We subtract the Milky Way model, and then we have the residual extragalactic Faraday rotation distribution left, which has a mean of 0 and a finite dispersion. And this dispersion is what we do our science with. So we're looking for the actual dispersion associated with extragalactic magnetic fields. Okay, and so luckily, this data set is actually useful for different types of studies. So studying the actual radio galaxies themselves, finding new pulsars. So there's a few highly polarized compact sources that turn out to be pulsars in this area of sky that weren't known before. But then most of the studies, at least that I've been involved with, are studying the magnetized properties of the extragalactic universe. Yes, and so we continue to process the data. And so hopefully, you know, early next year, we'll actually have pretty much the whole northern extragalactic sky Faraday rotation measured grid as part of this data release 3. Right, yes. So yeah, so it's exciting that we'll have a data set maybe 2 to 3 times larger than what I'm going to present in the rest of these slides. And just in case you'd like to see some of the radio galaxies and what the polarized ones look like. So this is just a standard LOFAR field, about 16 square degrees on the sky, a single 8-hour observation. And then the contours give you the synchrotron emitting total intensity contours of the radio source. And then the colored pixels are the region of the source that has detectable or detected polarization and its associated Faraday rotation. So you see most of them, the polarization is actually detected from the extremities, and they look like these Faranoff-Riley type 2 radio galaxies. But it's not exclusively those. Blazars still sneak in there, and there's a few FO1s as well. Okay, and in terms of if you're interested in downloading the catalog and using the data for your own science, so we do have a whole load of columns that, you know, provide some additional information, such as the linear size of the sources, their luminosities, some effort to automatically classify their morphologies, so that you can pick out maybe just the compact sources or just the extended ones. But the majority of ones that are polarized are resolved. So they're these nice double-lobed radio galaxies. Yes, and then of course we put huge effort into actually identifying the host galaxies and finding redshifts for these sources, because this really enables us to do our science. And so the polarized sources are the brightest ones, so they're more or easier to identify the host galaxy because of this exceptional image fidelity that LOFAR actually provides as well. So it recovers both the diffuse emission of the lobes as well as the compact emission. So it makes it much easier to identify the host galaxy. Yeah, that's a nice example that the host is here. Right, and so the median redshift is about 0.6. This is including the photometric ones. They're usually large radio galaxies, a median size of 400 kiloparsecs, and quite luminous, you know, above this FR1, FR2 luminosity threshold at 150 megahertz. And yeah, if you're interested in blazars, you know, there's interesting sources here where you actually, not only are you detecting the core of the blazar, but actually the extended, you know, kiloparsec scale jets and lobes in some cases. All right, yeah, and more new pulsars. Okay, so then for this second part of the talk is to focus on the science and just some of the recent results using this catalog. Mainly this work of Heeson et al. and a series of papers by Ettore Ferretti. And then towards the end, I'll mention the POSSUM results. Okay, so the first neat result was actually detecting the magnetized CGM in a bunch of nearby galaxies. So again, doing this statistically, we have our, you know, a whole sample of galaxies, and then we have some impact parameter of the rotation measure to this galaxy. And then we're trying to see if there's a signature of the Faraday rotation as a function of this impact parameter. Right, yeah, so 183 nearby galaxies selected from this Palomar sample. So they're all within 100 megaparsec from us. Yes, and then the key plot here that I'll take a few minutes just to explain. So always what we're looking for is this, you know, this excess in RM dispersion, you know, from a particular target or series of targets versus like a control or just the background level. And so, okay, yeah, you have the RM dispersion, and then this azimuthal angle is the actual azimuthal angle of the nearby galaxy. So an azimuthal angle of 0 means the impact parameter is along the minor axis of the galaxy and 90 along the major axis. And so beyond impact parameters of 100 kiloparsecs, it doesn't matter. oh yes, beyond, oh yes, the blue and the black here, the excess or the RM dispersion is the same for all azimuthal angles. And this RM dispersion actually matches, the actual background. So there's no, association of excess Faraday rotation related to the galaxies. But then within 100 kiloparsec and at small azimuthal angles, you see an excess of the Faraday rotation over the actual background level. And so it's this excess, so the difference between this red point and the blue and black points here is what we're saying is associated with the CGM of these nearby galaxies in a statistical sense. Right, and so this rotation measure excess of about 4 radians per meter squared then corresponds to about 0.5 microgauss at, say a distance of 50 kiloparsecs from the disk of the galaxy. And so this is interesting because we think we're now probing these magnetized outflows that are preferentially along the minor axis of the galaxy. And so this gives us a nice probe of, this baryon cycle or these inflows and outflows that are expected around, all galaxies. Right, and so, there's, simulations of these magnetized CGMs. And then what we think we're probing is these magnetized winds and outflows. And this is very helpful because there's not that many, observational constraints of the properties of the CGM. So it helps constrain these simulations quite well. Okay, and so then jumping from nearby galaxies to the largest scales to these cosmic web filaments, we then do a similar statistical study, so using the same RM data set, but now we have, we're using the redshift of the sources, and we're using, 1,000 of these where we have spectroscopic redshifts. And so what we're looking for now is an excess in the RM dispersion associated with cosmic web filaments. Right, and so this plot on the right here, this shows, so every blue dot here corresponds to one of these 1,000 sources and their redshift. And then the y-axis is the actual number of filaments intersected by those lines of sight. So from the radio galaxy along the line of sight, say for this one, there's 0 filaments identified from these optical spectroscopic catalogs. Whereas in these higher redshifts, then you're crossing, 20 or 30 filaments as identified in these catalogs. And so then, we want to look at how the Faraday rotation dispersion changes as a function of redshift of our sample, knowing the number of filaments that are crossing these, that this radiation is crossing. And so we have some theoretical expectations for how the Faraday rotation measure dispersion should increase, and we can parameterize it in a very simple manner. And this is, one of the early results where we looked at the dispersion as a function of redshift. And there's a bit of a caveat here that we're now assuming essentially that all of the Faraday rotation is dominated by the Faraday rotation from the intergalactic medium. We have other evidence to suggest this is not a bad assumption, but this allows us then to actually fit this very simple model to the observed data as a function of redshift to actually determine what, say, the characteristic or RM contribution is of an individual filament. And so the best fit result here shown by the orange line gives 0.7 radians per meter squared as the, a contribution on average from one filament. And so then we can do a back of the envelope calculation for a particular cosmic web filament density and path length through this filament and find a magnetic field strength in these filaments of order 30 nanogauss. Right, so this is already exciting, but then we can, this is a very, very simple calculation, but then we can do like semi-analytic models for the actual density distribution along the line of sight through the universe, as well as using results from cosmological, MHD simulations. But they all return somewhat similar results. So depending on the actual exact model we use, you can go from 10 to 40 nanogauss co-moving. So this at redshift 0 for the magnetic field strength of these filaments. Okay, I mentioned that we assume that the majority of the signal comes from the intergalactic medium. So we have some strong evidence for this in terms of, comparing our observations with observations at centimeter wavelengths, where and looking at what objects or what structures exist along the line of sight of our particular targets. And so the majority of the LOFAR polarized sources avoid galaxy cluster environments. So less than 10% actually fall within the virial radius of a galaxy cluster that happens to be along the line of sight. So this is one of the reasons why we don't see as many polarized sources at low frequencies, is because of an effect known as depolarization, which just removes the polarized signal if it happens to pass through some dense region of the universe along the line of sight. So LOFAR is providing us with this filter of, for dense regions of the universe, so we're only seeing the quite underdense regions. And then we have other ways of studying what's happening local to the radio galaxy. So I showed you this Fornex A image at the start, which had this very nice, complicated RM structure. And we believe that this is less than 50%, this local to the source contribution is less than 50% to the total RM dispersion that we measure. Okay, and now once we have this understanding, now we want to compare this more closely with cosmological MHD simulations that have different assumptions for the origin of cosmic magnetic fields. Right, and we do the same sort of filtering, so we don't select lines of sight that pass through a cluster in these simulations, so we fix it to a certain overdensity. Okay, and so this is the result, which is a very complicated plot. I need to maybe remove some of these lines, but I'll go through it again. On the y-axis, we have this RM dispersion as a function of redshift. And now the black points are the data points from LOFAR, but with this local contribution subtracted. So we believe that these black points, as accurately as we can, represent the contribution from cosmic web filaments along the line of sight. And so there's, the black points are the data, and then the other colored points are the results of, doing the same analysis, but through these, using sightlines through these MHD simulations. And then there's a whole series of models which we compare to for the origin of cosmic magnetism. So one is that you have a large-scale uniform field in the very early universe, and then you just evolve this passively through structure formation, so the field gets larger as things through collapsing structures, and gets weaker in the expanding voids. And so the gray points here are the prediction from the simulation for a uniform primordial magnetic field. And so you can see immediately that this is in conflict with the actual data at the higher redshifts. So for this particular model, it has a seed field of 0.1 nanogauss in the early universe. We can rule this out. And so this is interesting if you remember from the first slide one of the first slides where I showed the limits from the cosmic microwave background. So now we believe we're doing better than the limits from the cosmic microwave background, that we can actually rule out things about 10 times, or magnetic field strengths about 10 times lower than this. Yes, and then there's many other models here. So all these ones with this alpha S are parameterization of the power spectrum of the primordial magnetic field. These astrophysical ones mean that it's dominated by just outflows from galaxies. So you have basically zero magnetic field in the early universe. You have some battery mechanism that generates fields on small scales. This is amplified by some dynamos and things within galaxies and clusters, and then ejected into the intergalactic medium. And so this is what the astrophysical ones describe. And so, yes, and so this purple and brown ones are these curves here. So they can roughly match the effect at low redshifts, because now these structures have enough time to evolve and to pollute the environment, so that in the local universe, they've expanded their influence to quite large scales. But in the early universe, they just haven't had time to do this, and they underpredict the amount of Faraday rotation that one would expect. And so most evidence is now pointing towards these primordial magnetic field scenarios as being the ones consistent with our observations. And so this one is this blue one with a particular power spectrum behavior, which is kind of more towards the side of some inflationary mechanism. So where you have most of the magnetic energy on the large scales are these negative indices, and the positive indices are most of the magnetic field energy is on the smaller scales initially. And so the one that's most consistent here, the blue one, the pink one is pretty much the same, except it has this included contribution of the astrophysical scenario, which you can't really see, but provides an excess here at low redshift over the blue one. And then we can say that this is consistent with a primordial field of 0.4 nanogauss, an RMS value on megaparsec for a megaparsec scale coherence link. And so these astrophysical scenarios, at least in these simulations, are disfavored, and yeah, excitingly, it looks like these primordial fields are good candidates for the origin of cosmic lights. Okay, before I move from LOFAR to ASKAP, I just wanted to mention very briefly that we have this, LOFAR is actually currently undergoing an upgrade. And so early next year, we plan to start this LOFAR 2 era, where the lot survey will be mostly finished, and we'll be trying to move to new surveys over the next 5 years. And this iLots is one of the proposed surveys to actually do a similar survey to LOTS, but instead of at a resolution of 6 arc seconds, we will have a resolution of 0.3 arc seconds over the whole extragalactic sky. So then we'll have matched resolution images with the likes of the optical space missions like Euclid. And this would be by far the deepest and highest resolution wide area radio survey ever. So basically, because of this resolution, we would resolve basically all AGN jets on kiloparsec scales, while still be sensitive to diffuse emission. So LOFAR is this incredible imaging instrument where you can recover all these diffuse filamentary structures of radio galaxies, but also have the resolution to image, these very bright regions as well. And we're hoping we will find more polarized sources, because we have demonstrated that this is possible at the highest resolution, but it's still TBD to see how many more sources we will actually find. Right, and in the northern sky, we do have the access to these very good optical spectroscopic catalogs and surveys, so we can really do a lot of good science with the radio galaxies. Okay, and just to finish with, I will mention the Australian Square Kilometre Array Pathfinder. So this is in particular, this is at centimeter wavelengths with a very large field of view, so it surveys the sky very quickly. And in particular, the polarization survey is ongoing, and so for the next few years until 2028, and we're surveying basically the whole southern sky. So about 20,000 square degrees at a 20 arc second resolution, and now we expect to get up to 1 million rotation measures. So LOFAR is struggling with its 2,500, but this gets 1 million. And so one of the neat early results from POSSUM, so using less than 10% of the survey, and studying 55 galaxy groups, we're in the local universe, so at low redshifts and with this particular range in mass, and just as they happen to overlap with the kind of random observing patterns. So the blue means these are the data that have been publicly released and are accessible to the collaboration. And so again, we do the same sort of experiment, but now we're using galaxy groups and a separation or a distance criteria from these galaxy groups. So this flashback radius is basically giving you a radius of extent of the gravitational influence of these galaxy groups. And then we're plotting the RM dispersion as a function of this radius. And then, the background here is a similar background as we mentioned before. And so we're looking for excesses over this background. And so what's neat here is that within these first couple of flashback radii, we have this excess over the background. And this, we believe, is related to the hot intergroup medium with this particular level. But then even more excitingly is that we think we're also seeing the actual cosmic web filaments that are feeding into these galaxy groups. So on these larger splashback radii outside the virial radii of the groups, we also find an excess, about 4 sigma here. And so we believe this means that we're looking at this kind of denser region of the warm, hot intergalactic medium of these filaments feeding into these galaxy groups. And so then we can, with some simple calculations, we can estimate then that we're seeing magnetic field strengths ranging from about a microgauss in the hot intergroup medium out to, a 1/10 of a microgauss in these filaments feeding into the groups. And so the idea from, simulations here is you have these dark matter halos for the group. You have this hot medium, out to some fraction of the virial radius or a bit larger. And then you have these filaments of the cooler, warm, hot intergalactic medium feeding these galaxy groups. And so this is really exciting to be able to see this now at centimeter wavelengths as well for, a small sample of objects. And just if people are interested, so this is a very open and a very friendly collaboration, and we're only getting started. So if you're interested in using our data for your science, please do get in touch. You can find details at this possumsurvey.org. And so now we've up to about 200,000 RMs, which is, at least 4 times more RMs than have been detected in the history of radio astronomy. So already within 1 year, we have, a huge advance in our capability of studying the magnetized universe. And this shows you what's currently available if you get in touch. So we have this bunch of fields, and these colors just indicate the Faraday rotation measure of these fields just randomly scattered throughout the observing footprint. So here is your galactic plane where you see an excess in the Faraday rotation measure, and then your higher galactic latitudes with lower amplitudes. Right, and there's also a SPICE RAX one. So it's much shallower observations, but it will go up to +50 declination, whereas in POSSUM just goes to declination 0. So SPICE RAX will have this large overlap with LOFAR, and so I'm particularly interested in that. And so there's a public data release 1 of 13,000 square degrees, but the data release 2 will cover the whole sky visible to ASKAP. Okay, and so just to finish, so I hope I've convinced you that this Faraday rotation effect is quite a very sensitive, and this is kind of a new tracer or new precise tracer of diffuse magnetized gas from scales from the CGM up to the larger scales in the universe in these cosmic web filaments. We have this publicly released rotation measure grid catalog with LOFAR, which has been used to do interesting science. And we also have this POSSUM project ongoing, which is really, going to revolutionize our field. And so, and I think we're reasonably confident now that these radio data observations in combination with the gamma ray observations really do favor these primordial magnetic field scenarios, which is really exciting for people who study early universe physics as well. And we'll have lots more data in the future. So about 3 times the area with LOFAR pretty soon by the end of the year. And then we hope to expand this, to the very high resolution imaging. And then we have these exciting results from coming out from these centimeter wavelength telescopes, the SKA Pathfinders and others. And scarily, the SKA is actually now, starting under construction. So it's going to become a reality pretty soon towards the end of this decade. Okay. Yes, and if you're interested, and get involved in the SKA, so Spain is a full member of the SKA, so there's lots of opportunities now for people to actually, to lead science projects and to contribute to science projects with the SKA. So do get in touch. We have this SKA Cosmic Magnetism Working Group. So if you're interested in cosmic magnetism topics, please do get in touch with me or with the from the website. You can get the emails of the co-chairs. And there is a data challenge coming up sometime next year. So it'll be exciting to see what we can do with this. And this is very much at the preliminary stages. So there's nothing defined in terms of exactly what we're going to do and who has who gets time on the SKA telescope. So this is all to be decided in the next years. And so it's a good time to join, because also in the middle of next year, there will be an update of the actual science cases associated with this conference in the middle of next year. Okay, so yeah, thanks for your attention, and I'll stop there.
Thank you. Thank you very much, Shane. So if anyone has any questions or comments, discuss more details, any information. Maybe a question would be what is the main uncertainty or the main bias that you may have in measuring these filaments? What would be the main uncertainty or bias when measuring the magnetic filaments?
Yeah, so we worry a little bit about this this Milky Way model of the rotation measure that we subtract from our data. But we've done lots of tests, to think that we're relatively confident with this. But I think, these new Pathfinder experiments, as we have this very high density of Faraday rotation measures on the sky, we will be able to constrain the Milky Way contribution much more robustly. And this will, in turn, lead to much more robust and more confident conclusions about the contribution from filaments. And then on the other side is the actual local contributions to the sources themselves. And again, we will learn a lot. We think we have it reasonably well understood now, based on the combination of studying LOFAR or Metre wavelength observations with centimeter wavelength observations. We get an idea of what sources are being probed by both wavelength ranges. And but there's still a lot to learn about the local source environments and the Milky Way contribution, and this will then affect what we conclude about the intergalactic medium.
Are you using, or can you measure the galactic plane directly? But most of the survey is covered outside the plane of the Milky Way. But can you infer more information from data under?
Not really. I think the main advances will be at high galactic latitudes, and our techniques for subtracting the Milky Way, we know they don't work very well close to the galactic plane. So even when we have these models of the Faraday rotation of the plane of the Milky Way out to about 20 degrees from the actual plane itself, you get an excess residual Faraday rotation that's inconsistent with the large or with the halo. And so I don't think it'll be a long time, if ever, if we can use lines of sight through the galactic plane to actually study the extragalactic measure.
Yeah, thank you very much. That was a very nice talk. If you could go back to your plot, your slide about the rotation measure grids.
With LOFAR, or?
I think it's way back in the RN grid that we showed before, with the positive and negative currents. Yeah, exactly. I may be wrong, but it seems to me that the high positive iron values seem to favor some regions. For example, in the upper left corner, for example, is it some kind of, is it random, or is there some kind of explanation behind that?
Yeah, so it's not easy to see in this equatorial projection. So if I change it to galactic coordinates, you will easily see the pattern where you have larger circles as you go towards the galactic plane. So this red region here where the circles get larger, and these blue regions here, these are actually closer to the galactic plane than these regions here. The sign changes are just related to some maybe magnetized bubbles or structures in the Milky Way ISM, probably quite local to us. And so there's a whole other group of people who study the actual magnetic field properties of the Milky Way in the halo with these data as well. But we're we're for the purposes of our science, we're just trying to remove this signal as well as possible.
Okay, and one question related to that. So with the upcoming SKA grid, do you expect the southern region to be similar to this, or is that going to be different?
Yes, it will be many more data points. So you will be able to map these filaments, you know, and these weird structures a lot more in a lot more detail. But yes, so it's basically the net or the average rotation measure will have a similar statistical properties in the southern sky away from the galactic plane. So it's the galactic halos in both sides that are most useful for extragalactic studies, because there's not such a complicated contribution through the halos, and we hope that we can remove this relatively well.
Thank you very much again for the nice talk. My question is really perhaps related to the splashback idea that you have mentioned there. That I don't know if it is related to the QU fitting of the spectra to extract the different components in the rotation measure spectrum. Am I right on that?
No, so it's the dispersion that we measure is the dispersion between different lines of sight, so different locations on the sky. It would be super cool as well. We hope in the future that we will have the dispersion for each individual source, and so then we can have the dispersion of the dispersion, but the dispersion really from the QU fitting will give us the local source properties by and large. The local environment properties, and so this will be a very helpful way of checking that we're not making some erroneous assumptions about the contribution of the local the environment of the local sources.
Okay. And then perhaps the second question would be by using the QU fitting that you can differentiate between different sources of rotation measure. Is there a technique to use information on redshift so that perhaps you can make a measurement of rotation measure and therefore of magnetic field along the line of sight in cosmological distances, so that, I mean, in the end you would be able to construct 3D mapping of the magnetic field in the universe.
Right. So people are investigating this, but I think it's very unlikely to occur for individual lines of sight, because we basically have to get multiple components to be able to separate the RM structure along the line of sight. You need emission at multiple locations along the line of sight. And so we only have the polarized emission of the background radio source, and then it's only Faraday rotation along the entire line of sight. If there happens to be synchrotron emission from, say, this diffuse medium in this galaxy group, then yes, we could use the QU fitting to say, okay, the background source has this Faraday rotation measure up until the group, and then the emission from the group, we can separate that and then say, oh, the group has the Faraday rotation signal from the group to us. But we still end up with a similar problem, that we have the whole intergalactic medium between the group and the source and the local source environment, and we have the Milky Way in the foreground. So I don't think the QU fitting will only help us in understanding the local source contribution, because in many cases we're just averaging over the whole source, and so we might have two lobes, and so you imagine you have two polarized sources, and then you're averaging them, in a incoherent way within the beam of the telescope, and then this can produce kind of spurious rotation measures in some cases. So there may be a bunch of spurious rotation measures in these data sets that we can actually remove or better quantify with this QU, this polarization model fitting.
Thank you.
Thank you, Ivan. So I think we have two questions online. Miguel, can you unmute yourself and
Yeah, can you hear me?
yes.
Okay. Well, thanks a lot, Shane. Very nice talk. So I have two questions. My first one would be is related to this huge difference between the limits you are obtaining. So B field something like less than 0.4 nano Gauss, and then you mentioned that there is, you know, it must be larger than 10 to the minus 7 nano Gauss. So what is then what do you envision as the ways forward to really constrain better those limits, or to come to some value that say, well, it is within, I don't know, 10 to the minus 2 nano Gauss? And so is there any?
Yes, yeah, so yeah, great question. So for magnetic fields in voids, the radio observations, I had it somewhere, but I didn't explicitly say it. They will probably never help us for magnetic fields in voids, because the density of gas densities are just too low to detect appreciable Faraday rotation. However, the Cherenkov telescope array should dramatically improve the lower bounds. And so we're hoping that, you know, the Cherenkov telescope array might actually, instead of having a lower bound, it might actually detect the magnetic field in these voids. And so that would be super exciting, because we would have a detection of magnetic fields in voids from gamma rays and a detection of magnetic fields in filaments with the radio telescopes. And then we really would have, you know, two data points that we could then be fitting, you know, all our primordial magnetic field models to, and we wouldn't be working with these lower and upper limits.
Oh, that would be lovely. So, and then the other thing is more, you know, of a physical nature, because to be honest, I am a bit lost with this, again, 10 to the minus 7 nano Gauss. It's really 10 to the minus 16 Gauss. Cannot even imagine this. So what can we learn about maybe inflation, or, you know, in a more cosmological term, when once you, let's say, okay, it's 10 to the minus 6 nano Gauss, or it's 10 to the minus 2, what are the implications in terms of cosmology?
Right. And so, yeah, so in the voids, yes, it's 10 to the minus 6 nano Gauss, say, but in the very early universe, because of the expansion, or just the inverse of this, you end up with micro Gauss level fields, you know, during the epoch of inflation or something like this, that some of the models predict magnetic fields that could be strong. And magnetic fields that are this strong in the early universe can actually, you know, it's a plasma, and they disturb the plasma. And the production of magnetic fields disturbs the plasma and then generates these gravitational waves that might be the actual explanation of the stochastic gravitational wave background. So that's one of the kind of exciting insights that you can gain from determining if, you know, inflationary magnetogenesis models are actually the most likely scenarios. And if they're not, then you end up, so these are where you have large amounts of magnetic energy on the largest scales. And then there's the kind of what are called causal mechanisms, which happen a little bit later in the universe, during these, what's it called, the electroweak phase transition epochs. So where you have the fields generated, yeah, when you have, you know, matter forming, and yeah, so people have models for, you know, magnetic field strengths generated during this epoch. And so it gives some insight into whether those theories make sense or not, or, you know, what you have to add to them to explain the observed level of fields. So basically, you know, it's exciting. Yes, these primordial fields, people say they might become a new, you know, extra pillar of cosmology, because it helps us probe the physical properties, you know, before recombination, basically. And there's very few ways we can actually probe the universe before recombination.
Okay, so thanks a lot for the clarifications. Yeah. And so my other question is related to this graph where you show the rotation measure versus redshift for the LOFAR data, and you have these different models with alpha being different and then uniform, etc. So here with the best fit, you know, which is okay for, let's say, relatively large redshifts, but at very early redshifts, or sorry, small redshifts, you have the measurements are really way above this feed. So is this due to some specific filament? Is it just, you know, the uncertainties are larger than the ones you are drawing here? What is going on here at early redshifts? Because even, you know, all the models, no model goes, you know, fits that, or the data doesn't.
Exactly. Yes. No, yeah, this is a great point, and I didn't mention it. These wiggles are, well, what we call these wiggles are just the
that's
kind of jumping around like this. And so we've tried to understand whether these are, you know, real or just statistical fluctuations. They do correspond, the dips correspond to overdensities in like photometric galaxy counts along the line of sight. But we can't really, at the moment, come up with a plausible model to explain them in terms of, you know, the magnetic field properties or the gas properties along the line of sight. So what's not in these simulations are, like, you know, some sort of supercluster along the line of sight or the local contributions of the sources themselves. So that's what we may be, still maybe remaining in our data at the lowest redshifts, where we have possibly the largest, you know, contribution from the local source environments. And because what you cannot see here very well was this pink one was an effort to have this astrophysical model combined with a primordial one. And the pink one has this excess at low redshift relative to the blue one, which is just the primordial one. And this was an effort to try and see, oh, can we get a higher value to actually explain the data? And at the moment, we cannot. So we're still unsure at these lowest redshifts, what the explanation for this excess might be. It's exciting if these actual wiggles are real, and so then it can actually tell us something about, you know, the structure of the universe at these, you know, lower redshifts.
Thanks a lot. Very nice. Thank you.
Okay, I think we have a last question from Janis.
Yes, thank you very much, Shane, for the nice talk and the very interesting results. So my question is about the LOFAR RMs. You mentioned that they are sensitive to the lower values and also they have much less uncertainty. This is very interesting. And I like what you said, that it's a filter for the higher density structures. So I understand that higher densities and higher magnetic fields both can cause higher rotation measures that would depolarize the LOFAR signal. My question is, do you think, from your experience, is there any possibility to differentiate between, to disentangle the two sources of increasing the rotation measure, namely the density and the magnetic field, for example, from your experience in LOFAR?
So this is what we try to do with the estimates of magnetic fields, if I understand your question correctly. So the rotation measure is the integral quantity of the density and the field. So we just get that combined quantity as the measurement. And then all our magnetic field estimates are model dependent estimates, because it's a model of the electron density, which is kind of easier to model because we know a lot more about the gas density properties of the universe. And so there's several ways of going about this. The most complicated way is using the densities from the cosmological simulations. So we get, you know, a statistical estimate of the density along a particular line of sight. So doing it for individual lines of sight, I think is very challenging. So most likely we'll just be able to say, you know, statistical things about, you know, the magnetic field properties of at a certain overdensity.
My question was on the more on the observational side. So not on a statistical phase, but you see these radio galaxies that you have signal on the outskirts because the density, the magnetic field probably drops, but at some point towards the core, you lose the polarized signal, and this can happen with both reasons. And my question is if you have looked into this more line of sight dependence of the disentangling these two effects.
Yes, so
individual sources,
right. So what we will need to do is combine the LOFAR or meter wavelength observations with centimeter wavelength observations. So the meter wavelength observations will just give us the small patches where the the depolarization is very low, and then the centimeter wavelengths will allow us to map, you know, almost the full Faraday structure of individual radio galaxies. And so we can actually select, even in the centimeter wavelengths observations now with the likes of POSSUM, we will be able to select sources that have similar, you know, depolarization properties as LOFAR, so that we can actually, cross-check our understanding of whether, whether we understand the rotation measure properties of the population of sources that we're detecting with LOFAR. And for individual source studies, the centimeter wavelengths are still probably better because they will detect the Faraday structure, you know, of the whole source itself.
Thank you. Yeah, this combined analysis, it looks interesting. Thank you very much.
Okay, I don't think there are any other questions, so thank you, Shane. I think we can thank the speaker again.